So good afternoon. This will be the first session ever of this seminar in English. Just decided. And today's speaker is Ramón Plaza from the Institute of Applied Mathematics of UNAM. And today he will speak about diffusion limits of velocity jump processes for biological agents.
Okay, thank you very much for the invitation. Thank you, Alessio, and all the organizers. This is the first time that I speak here, and I'm very happy to be here because this is like home, actually. I studied here, of course. And lucky me that I prepared the slides in English, and I'm going to be the first ever speaker to deliver the talk in English. If you have any questions, or if I speak too fast or anything, just let me know. I'm going to talk about, as the title says, about diffusion limits of velocity jump processes for biological agents. I'm going to talk about a very precise model, like motivation, in order to present the method. And I'm going to present the method in a very thorough way. I'm going to do all the details just to communicate how this method works. And the idea is to derive mean field equations for some biological models, starting from stochastic processes that are called velocity jump processes. Okay? So I'm going to do all these derivations so that you have a feeling of the method, and I hope that you find it interesting. Okay, so first let me start with the motivation, the specific problem that motivated all this study. And it's about the dynamical patterns, the spatial dynamical patterns, I would say spatial and temporal dynamical patterns of certain strains of bacteria that you can observe in experiments when they are put in a petri dish. Okay? So bacterial colonies in vitro exhibit these aggregation or diffusion patterns, which are very complex. Usually these patterns are the result of very hostile environmental conditions. So they put very little food for the bacteria, or the substrate, usually agar, is very hard, for example. And still the bacteria have very, very interesting, complex ways of interaction that produce these complex patterns. They are not dumb at all. They exhibit lots of complex self-organization mechanisms, for example, at the micro level, which is cell-to-cell communication, or the macro level, which are chemical signals and some receptors from the bacteria. They communicate from one part of the spatial domain to the other, even exchange of genes, etc. And let me give you an example. The strain of bacteria Bacillus Subtilis, which is very common in experiments. This is a gram-positive bacterium, broad shape, as this shape like a Twinkie. You know what I mean. They have a protective endosperm. Twinkie is a little cake that was very popular when I was a child. They have a protective endospore, which is kind of protection on the coat that makes these bacteria very resistant to very hostile environmental conditions, and is flagellated. So that means that they are very receptive to changes in chemical signals in the environment. And in the usual experiments that you can find with this bacterial strain is as follows. So you have a petri dish with a substrate, usually agar, and they put some food, which is usually uniform concentration of amino acids, for example peptone, and they inoculate in the center of the petri dish with some strain of this Bacillus subtilis. These are the experiments of the Japanese group of Hiwari in the early 90s. Okay? So they inoculate in the center of the petri dish, and these bacteria start to consume the food and to start to form these very complex patterns. So there are many observations, there are many regimes, depending on the temperature, depending on the hardness of the agar, depending on the level of nutrient, that determine how these patterns evolve. Let's suppose that the temperature is is constant. And we are going to vary only the agar, the substrate, hardness of the agar, and the level of nutrient. So for example, in the low nutrient hard agar regime, they found these diffusion limited aggregation patterns. These are the experiments of Matsuyama and Matsushita and the group of Eshelbey Jacob in Tel Aviv University. And the patterns that these bacteria form are usually fractal. They are very dendrite-like, and the dimension of the envelope from in the case of high nutrient, or the dimension of the dendrites is usually fractal. The geometry is very, very specific. In the semi-solid low nutrient regime, this is called the dense branch morphology regime, the DBM regime, and this is the regime that I'm interested in. You have usually a smooth colony envelope. If the nutrient is very low, then the bacteria form dendrites. But the boundary of the envelope from is smooth. So in this regime, this is the regime in which you can propose, for example, a PDE, a differential equation, in order to model these dynamics. The high nutrients of agar is the best possible scenario for the bacteria. They have lots of food, the agar is very, very soft, and they crawl very happily. And this is going to be the region D, okay? And you have transitions between these regions, and we are going to use two parameters. One of them is the concentration of the nutrient, and the other is the agar concentration. The softness of the agar is measured by 1/0A. Okay? So these experimental observations are usually put in what is called a morphological diagram. So in the case you have the agar very, very hard and very low nutrient, which is the region A, you have these fractal patterns. This is basically like this. Okay? If the agar remains very hard, but the nutrient goes up, then you have this region B, in which you have, an envelope from, but the dimension of the envelope is fractal again. I'm interested in the transition between region E and region D. Region E is when you have soft to medium agar and low nutrient. In that case, you have dendrites. The bacteria form like these little fingers, okay? But the envelope from is smooth. And if you go up in the nutrient level, then you obtain like a kind of a pizza, okay? Bacteria are very happy, they have lots of food, the agar is very soft, and they form these envelope fronts, which are like a pizza with the boundary very, very smooth. Okay? So I'm going to be interested in this regime, the transition between E and D.
What is the stripe regions?
I don't know. These are the stripe regions are like the transition regions between the experimental observations. The experiments are basically A, B, C, D, and E, and you have transition in which it's not very clear what happens.
What is the reference? What is the reference of this figure?
In the literature?
Yeah, from which reference are these figures from?
These are pictures of the actual experiments, and they are here, region E and E. I didn't write it down. I don't remember for region B, which is
so
not here.
there are different references.
There are different references. Yes. Yes. In this case, this is a dense branch morphology. The experiments of Ohiwari. Okay. And how to model this? How to model the dynamics, which is very good. So there are many ways to do it. Let me mention two of them. You can consider bacteria discrete agents. So in this case, you have an agent which is basically one cell. It's a self-propelled particle, self-propelled agent. They move, they interact with the environment. You have a rule for the movement for each individual cell. And they consume nutrients, etc. And these kind of models are suitable in order to track the internal state of the bacteria. If they die, if they change their composition, etc. Another type of models, which is the starting point of the study, are bacteria as continuous densities. So you can suppose that the number of bacteria is approximated by a smooth function that depends on space and time, and you propose a set of partial differential equations, usually systems of reaction, diffusion, or other transport terms type of equations to model the dynamics. Okay? In that case, all the constituents of the model, bacteria, chemical, and other agents are considered as densities. Okay, so let me focus on experimental observations in this DBM regime, which is basically the work by Ohiwari and collaborators in the early 90s. In the DBM regime, they observed that the bacteria are inactive in the inner part of the pizza, let's say, and outside. Outside, the bacterial density is very low, so that's understandable. But in the center of the envelope front, the bacteria are also very inactive. Okay? So that they are very active in the boundary of the envelope front. So cells become inactive again at the outermost front of the bacterial colonies, while the cell density is very low. Okay? So in order to model this behavior, Kawasaki and collaborators in the 90s as well, they proposed this nonlinear PDE reaction diffusion system of equations for this regime. Okay? So they propose a system of equations for the bacterial concentration, which I will call U, for the concentration of the nutrient, which is going to be P. This is a system of reaction diffusion equations. The interesting part of this model is precisely the diffusion coefficient that is associated with the bacterial density. This is a typical term of diffusion. You have the flux here, which is a diffusive flux, certain coefficient D times the gradient of U, and you take the divergence of that part. That's diffusion. Okay? So in order to explain this behavior, Kawasaki and collaborators propose this diffusion coefficient. And they say, okay, in order to explain this, we're going to propose the following diffusion coefficient. It's going to be proportional to both the density of the bacteria and the density of the nutrient. So that when the nutrient is very low, bacteria are very inactive. They don't diffuse at all. Or if the density of the bacteria is also very low, they don't diffuse. Okay? So this is, let's say, it's a diffusion coefficient which is non-linear, of course, density dependent, and degenerate. It's degenerate because when U or V are 0, then you don't have diffusion at all. And then it's going to be complemented by a standard reaction diffusion equation for the nutrient with constant diffusivity D for the nutrient, and a reaction term. The reaction term, which is a kinetic term, is going to measure more or less the probability of encounter between bacterial cells and food. And notice that this is some conservation form. So when you increase the number of bacteria because of encounters of bacteria with food, then you decrease in the same amount, more or less, the density of the nutrient. This is a model that proposed Kawasaki and collaborators, and they endowed this model with, of course, standard non-flux boundary conditions and initial conditions. What are the interesting features of this model? Well, conveys the motility of the bacteria precisely when U or V are low, and models high activity in the boundary only. Is valid only for the DBM regime, which is the transition between regions E and D in the morphological diagram, and it provides a complex dense morphology. Not only that, from the mathematical point of view, it is also very rich in structure, and it has been studied by Faustino, for example, and other authors, because of this degeneracy of the diffusion coefficient. Okay, yes.
So, very quick, I already forgot the experiments. The question is, so there's this assumption about the concentration of the agar. So the diffusion coefficient, the sigma, I think, in the diffusion coefficient is inversely proportional to the concentration of the agar.
That's right. Thanks
is
for
that in line with the experiment? With all the experiments? Because it seems to me that there was one that may have not been consistent?
That's a very important question. It's a very good question because it's precisely the motivation of the velocity jump processes that I'm going to present. Yes, exactly. The diffusion coefficient is this one. Sigma is a physical parameter. And they say, okay, sigma is going to be proportional to the hardness of the agar. If the agar is very, very hard, then sigma is going to be very, very low. If the agar is very soft, then sigma is going to increase. The question is, how do you measure this? It's not so easy. What are the units of this guy? So I will come back to this point, and it's going to be very clear when you see that from the perspective of a velocity jump process. But that's precisely the point of this. So what are the features of this model? I already mentioned them, and this was the motivation of the doctoral thesis of my student Francisco Leiva. So we started to review the literature, and we noticed that there's also an important factor that has to be taken into account, which is chemotaxis. So what is chemotaxis? The chemotaxis is the movement of biological agents towards some changes in the gradient of certain chemical signals. And this is a very well reported phenomenon in biology. You find chemotaxis in bacteria, of course. You find chemotaxis in the endothelial cells of tumors. The tumors segregate certain chemical, and then by chemotaxis, the blood vessels are attracted to the changes of chemical signals secreted by the tumor, and then the tumor gets vascularized. Okay? Also, some bacteria are sensitive to chemotaxis due to some other agents like fungus, and this is used in biocontrol. And the chemotaxis can be repulsive or attractive. So the cells or the agents direct the movement towards these high concentrations of the chemical, or to the contrary side. And this is a review of the literature that Paco did in his thesis. He noticed that in the particular case of Bacillus Subtilis, there are strong evidence that these are sensitive to chemical agents. So they show that the chemotaxis is observed in Bacillus Subtilis towards amino acids. For example, the peptone that they use as nutrient in experiments. And also, the role of chemotaxis is very strong in the formation of these patterns. Ben Jacob and his group identified 3 types of chemotactic signals. One of them is repulsive, which is in this long range, by starving bacteria in the center. So there are some bacteria that are dying in the center, and they produce some chemical signals that made the other bacteria that are more active in the outer region to be repelled. The other is attractive, is very short range, in which bacteria in the envelope front ask for help in order to metabolize waste. And the most important one is nutrient chemotaxis, or chemotaxis towards nutrients. So there is a nutrient, there is this chemical concentration, and the bacteria, they have these flagella, these receptors, and they sense the changes in the gradient of the chemical, of the nutrient concentration, and they direct their movement towards it. And the second important factor is that based on experiments, Ben Jacob proposed a relation between diffusion and chemotaxis in certain neutral regions. What is this relation? How do you model chemotaxis in a PD? Well, this goes back to the seminal work of Keller and Segel. So most of you know about it. So Keller and Segel said, okay, you have this diffusion flux, you have to add a chemotactic flux. And then you have to add the divergence of this chemotactic flux to the equations. Actually, this is not what Keller and Segel said, and this is a shortcoming, because they derive the equations using a special jump process, and they they say, okay, there is a relation between diffusion and chemotaxis. And in the same journal, in the second paper, they say, okay, we're going to forget about that, because if you consider that there are no traveling waves, so we're going to assume that these two fluxes are different. And if you look at the book, in the book by Murray, he says, okay, there is a chemotactic flux and there is a diffusion flux. Okay, so let's suppose that we are in the Murray mindset, and we're going to propose a chemotactic flux. The chemotactic flux in general has this form. It's going to be proportional to the gradient of the chemical, in this case the nutrient. And what is the constant of proportionality? Usually you have a chemotactic sensitivity function, which is a function of V alone, because it depends on the chemical under consideration. And Ben Jacob and collaborators proposed this other, they call it bacterial response function to the nutrient gradient. This is kind of phenomenological. They say, okay, let's propose it like that. And they say, okay, based on the experimental observation, in this regime that we are interested in, the bacterial response function has to be proportional to the diffusion of the bacterial density times the density of the bacteria itself. Why? That's a very good question, and this is precisely what I want to answer in this talk and to convey in this talk, how to justify this. They say, okay, it's because of experiments. Okay, let's suppose that this is true, and just let me give you an example. If you have the diffusion coefficient constant, okay, then using this rule you recover the standard Keller-Segel chemotactic flux, which is of the form plus or minus, depending on repulsive or attractive chemotaxis, then chemotactic sensitivity function, U times the gradient of the nutrient. So it's kind of agrees with the usual models of chemotaxis.
Is it correct to think that this is sort of assuming that populational stress in bacteria drives the movements of bacteria towards or in the direction of the gradient?
Again, please.
So, you know, one thing would be to say that there's stress, and because of stress, bacteria are going to seek and follow the gradient,
Right.
or or anything that they're pursuing. But there's also this population component in there, because the minute you put the bacterial density there, it would matter if there's a lot of bacteria in the same place and they're all stressed because they would move faster, for example, right?
Exactly. In this case, this observation is purely phenomenological and it's only valid in the DBM regime, in which U, the bacterial density, is usually low. Oops. Excuse me. So I guess that this has to be adapted to the case in which you have stress due to higher population, right? And maybe the sign has to be also involved if you are modeling aggregation, for example. Okay, so in this part of the doctoral thesis, doctoral project of Paco, so we decided to include a chemotactic term to the Kawasaki model and see what happens. No? So this was the first part of the project. So we added this chemotactic term here. Okay, why? Well, we wanted to be consistent with the observations of Ben Jacob, so we decided to be compliant with this observation, and the chemotactic flux has this form. It's going to be the chemotactic sensitivity function, which is of type of Lapidus-Schiller. This Lapidus-Schiller function is the receptor law, saying that, well, if the receptors of the bacteria are saturated, then they are no longer sensitive to the gradient. Okay? But more importantly, this is proportional to the diffusion coefficients times U. So that is why it's sigma, B, and U squared. Purely phenomenological. Let's see what happens. So, as I said, the bacterial response function is precisely like this. we endow the system with no flux boundary conditions and some initial conditions up to us. Let me say a comment here. This is the system in non-dimensional form, so the only free parameters that we have are precisely this sigma parameter, parameters of the agar, this chi 0, which is right, is a measure of the intensity of the chemotactic signal, is non-dimensional, and also the initial concentration of the nutrient is going to be another parameter. So the first thing that we did, so we performed some simulations. This is just how we did it. We used graphic processing units. These patterns are very complex, so you need high resolution in order to capture all the dendrites and the complex patterns. So we use graphic processing units. We use the simplest numerical scheme available. It's compensated by using very short time steps, because we have lots of processors working at the same time in parallel, so we can, in order to avoid stiffness, or to overcome stiffness, we can use a very small parameter time stepper. And we use a uniform initial concentration of the nutrient, and as initial condition for the bacteria, just a Gaussian. So you inoculate in the center of the Petri dish with a population of bacteria, it's just a Gaussian. Parameter values, this is important. We use soft to medium agar, this initial condition, and the chemotactic signal 0 and other positive values. So basically we reproduce the model of Kawasaki, and then we switch the chemotaxis on. So this is a picture that you don't see well, but this is the simulation with no chemotaxis. So this is basically the result of Kawasaki, and you see that the envelope front, this is the Devier regime, starts to grow because of the bacteria. They start to process nutrients, and they advance. Okay, you can see here some morphology in the colony pattern. You see some dendrites. Let's switch chemotaxis on. So if you increase the chemotaxis, then the first thing that you see is that the envelope goes faster. So it starts to grow faster. This is no surprise, because if there is chemotaxis and the movement is directed towards the nutrient, well, of course, they're going to go faster, right? But also, if you switch chemotaxis even higher, then you see that the envelope goes faster, and also you see a change in morphology, because the pattern becomes smoother. You could think that it becomes more stable. So these are basically the observations. This is the summary of this paper, which is in collaboration with Carlos Malaga in the physics department, and Paco Leiva, as I said. So we incorporated a suitable chemotactic term into Kawasaki's model to perform these high-resolution numerical simulations. A numerical observation is the following. There is a change in morphology. Patterns become smoother, less branchy, in the presence of chemotaxis. And we made a numerical estimation of the speed of the envelope front. We did some asymptotic, front propagation approximation in one direction, in the normal direction. We have a traveling wave. You can estimate the value of the traveling wave, and with these asymptotics, which are very good, but had a very good resolution with numerics, we proved that the that the speed of the envelope front is an increasing function of the chemotaxis. So if you switch chemotaxis on, then they go faster. The only thing that we could not quantify is why this change in morphology. But this was later on proved by my master students Alex Butanda. We could provide a quantitative argument of why this change in morphology happens. So we, in the geometric front propagation approximation, we linearize the equations around the envelope front, all in one direction. We disregard the transverse the component in the tangential variables. So this is an approximation, of course, but the perturbations can be multi-d. So we perform an energy estimate on the linearized operator around this envelope front, and we prove that the energy bounds for the eigenvalues are a decreasing functions of the chemotactic sensitivity, meaning that you need more energy in order to stabilize the patterns if the chemotaxis is high. Okay.
The sensitivity.
Excuse me?
The sensitivity.
Yes, the chemotactic sensitivity, exactly. Right. So what is the moral of this story? Okay, we have these models. They are all phenomenological, right? There are many parameters here that are very hard to measure. So how can we relate this PDE mean field microscopic model to some microscopic properties of the system? For example, like hardness of the agar, and why this relation between diffusion and chemotaxis. So it is very clear there are some situations in biology in which the diffusion coefficient, the diffusivity, is density dependent. There are many references has been observed in populations of mammals, cell biology, in ecology, etc. A non-biologically related example, which is very popular, is the porous medium equation. You have this diffusivity that depends on the density U. And what is the paradigm? You have this type of equations in which the diffusion coefficient depends on the density. How do we model this? How can we relate this with the microscopic problem under consideration? So this is what motivated. Yeah.
Before switching to the next part, this chemotactic component that you added to the model, a priori you could add many of them corresponding, for instance, to nice chemicals and bad chemicals, right? The study.
Right.
I don't know. Yeah.
Right.
You could add many terms of chemotactic corresponding to.
Exactly. There are basically three types of chemotactic terms. The one over the logarithmic function, the original by Keller and Segel, Lapidus-Schiller, which is receptor, and others that.
If you have more than one type of nutrients or in general chemicals, imagine you have U1, UV, U1, U2, and so on.
Okay.
And some of them are attracting, and some of them are.
Right. Yes. Of course, you can complicate the model. Yes.
Just,
Yes.
you could a priori study what happens if you have a colony of bacteria with one nice nutrient here, one bad nutrient here,
Right.
and show whether it actually goes toward the nice nutrients.
Absolutely. Yes. You can complicate the model as much as
Yes.
you want. Right.
Related question. I think it's more or less the same thing. Did you, or are you going to look at the relationship between the sensitivity for chemotaxis and the I don't know how to call it. The strength of the draw from the chemotactic element in here, because there seems to be this. So if you have more of a reason to pursue a gradient via bacteria, because you're stressed or whatever the situation is, but your sensitivity is low, then you may not be successful, and you may be more successful in a situation in which you're not that stressed, but your sensitivity is really high anyway. Right? So these are two possibly conflicting situations that may affect the patterns in opposite ways, because you make reference to the dendritic, the formation of the dendrites, but you also made reference, or that's what I thought, about the shapes of the possible branches that you form when you start forming the dendrites. And those go away when the sensitivity goes up, right? Because you get smoother patterns, but more direct patterns.
But only in the DBM regime, when the concentrations are low. For both bacteria.
Okay, and that has to do with your sigma.
Exactly.
Yes.
And the answer to your question is no. I'm not going to relate the diffusion with the chemotactic sensitivity. The chemotactic sensitivity depends on the chemical under consideration alone, so to speak. It's going to be related to the chemotactic flux. basically the bacterial response function that Ben Jacob invented has to have something to do with the diffusion. That's it.
And before that, you mentioned that you could model like eukaryotic cells with the same processes, but I think you have a lot of constraints in eukaryotic cells that doesn't exist in prokaryotic cells. Like, for example, the extracellular stiffness maybe is not the same like the agar stiffness, or even you have like ponderated zones of activity or migration, etc. Not all the cells migrate. All of them migrate in different ways. So maybe you could, if you are going to model eukaryotic cells by this way, we should couple them with dynamical patterning models. That is a theory by Newman and Batt that talks about all these reaction diffusion, etc. mechanisms of aggregation, but adds another typical of animals that could solve this problem.
Right.
So, because I think there's a big
Yes, of course.
drift between eukaryotic and prokaryotic cells.
Modeling is a serious business.
Yes, it is. I agree completely with you. And I just have to say that I mentioned eukaryotic cell biology is the work by Sengers and other authors as an example of a reaction diffusion system in which the diffusion coefficient has to depend on the density. Just an example of that. I agree. Okay, so oops.
If you're not busy, you have 1 more hour.
Okay. We can order pizzas.
Okay, you denied to give money for
That's right. So I will try to be quick. My idea is to present this method, and it's based on the. We'll try to model the dynamics of these biological agents by velocity jump processes. The main reference is by the paper by Othmer, Dunbar, and Alt in the late 80s, and they propose this type of processes in order to model the dynamics of agents. These agents can be particles, cells, microorganisms, etc. They make instantaneous jumps in velocity. Instead of making jumps in the physical space, they make instantaneous jumps in their velocity. So they are going with a certain velocity, and that with a certain probability, they change direction and change the speed. Okay? The probability distribution of time between turning events, which is the mean run time, is going to be 1 over lambda. This is the mean run time. And we are going to use a subset of allowed velocities, which is going to be a compact subset of Rn, symmetric with respect to the origin. Okay? And the probability of turning, of going from one velocity to the other, is going to be determined by a probability kernel, which is going to be this function t of v prime. This is going to be the probability density of turning from velocity v prime to velocity v, if a certain reorientation occurs. So the departing equation for this is a transport equation. I'm not going to talk about the details of the derivation of this equation. This was done first by Daniel Struck in the 70s. And this is called the forward Kolmogorov equation. This is similar as in kinetic theory of gases. You have a transport equation for the density function, which is the population of agents, more or less the number of agents at time t in a position x that are traveling with a specific velocity v in the set. So the evolution of p is governed by this transport equation, which has this form. It's going to be the rate of evolution of p over time is going to be governed by this transport. This is precisely the term that tells you, well, these are the guys that are traveling with speed v, minus some the guys that go from v to v prime, right, with mean run time 1 over lambda, plus lambda times the probability that your population from velocity v prime switches to velocity v.
G is going to be the reaction term, and we'll talk about it later on. And usually, we're interested in moments of this, velocity moments of this population P. The first or zero moment is basically the density of the population. Is the integration in all possible velocities of the population, right? And depends on x and t alone. So I'm going to present the method of Hillen and Othmer, and they propose a method. This is formal. This is not rigorous. It's just an asymptotic expansion of solutions of this transport equation, and they lead in a certain diffusion or hyperbolic limit to mean field equations for the densities. In this case, for the 0 or 1 or 2 order velocity moments. Okay. If you're acquainted with kinetic theory, this is precisely the Hilbert or outer expansion of solutions to the transport equations. So let's suppose that V is a symmetric with respect to the origin compact set of velocities, and for fixed x and time, you define this operator like this. This is an operator on functions that live only on the velocity space. And this is basically all the functions in L2 of B that are positive. And these are the four structural assumptions on the Turner kernel. For each t is a probability density, has to be greater or equal than 0, and the integral in B prime has to be 1. It's a probability density. If you integrate twice, it's finite. I will skip this. This is not important. This is interesting. You can specialize it to the orthogonal space of the constant, and this is a bounded operator. Finally, this assumption is a bit strange in applications, but in our case it happens. The integral with respect to B prime and not B. If the integral with respect to B is 1, the integral with respect to B prime is also 1. Okay, let's assume this, and you define which is the Turner operator, which is this. This is a linear operator. Lambda times p is a function of B alone, and this integral operator. Yes.
The boundedness hypothesis is because of stability.
Right. Because of stability.
If it's unbounded for only small subset in the orthogonal of constants, does it work?
No. No. It's to be bounded. Yes, sir. I cannot think of any physical application of, but it could be, I don't know, unbounded operator. I don't know. Okay, so this is basically the mathematical machinery that we need. This is the most important property. Under these assumptions, mu equals 0 is a simple eigenvalue of this Turner operator. And the eigenfunction is constant. And another important property is D. When you restrict this Turner operator L to the orthogonal space of the constants, then it has a linear pseudo-inverse F, which is a bound operator. All right. So this is a fundamental assumption in the modeling processes. We're going to assume the parabolic scaling or diffusion limit, meaning we're going to assume there exists a small parameter epsilon, such that if we make this scaling, tau is going to be the slow time, it's epsilon squared t, and psi is going to be epsilon x. This is a parabolic scaling. Then tau and psi are of order 1 when epsilon goes to 0. And in the case of bacterial movement, this happens, for example, in the case of Escherichia coli. Characteristic speed is around this value, and the mean run time, which is measured in experiments, is around 1 second. So for E. coli, you have that epsilon is 1 over 100, more or less. And for Bacillus Subtilis, we have similar measurements. Okay? So let's say that for the specific problem that we want to model, we're in this regime. We are in the diffusion regime. Let's suppose this. This is the important assumption. So if you assume this, then you can transform your transport equation, and you obtain an equation which is rescaled. It's a new forward Kolmogorov equation, rescaled, and has this form. Let's forget the kinetic terms for the moment, and you have this form. So what is the method in a nutshell, in a few words? The method means you're going to propose a solution to the rescaled Kolmogorov equation in terms of an asymptotic series, a series of powers of epsilon. P0 is going to be the dominant term, plus epsilon P1, plus epsilon P2, etc., etc. This is formal. This is not rigorous. We don't know if this converges or not. Let's suppose that this works. We're going to plug this solution into the transport equation, and we are going to look at the hierarchy of equations that results from collecting powers of epsilon. Okay. This is basically the method.
Are there ways a posteriori to verify that?
Yes, of course. Yes. A posteriori, you can say, okay, let's suppose that I have a solution of the transport equation of the velocity different processes with some boundary conditions and initial conditions, and if epsilon goes to 0, they converge. You can prove rigorously. We have not done that in this case, but in kinetic theory, this is what usually not. Then you prove rigorously that they converge to the solutions or weak solutions to the mean field equation. Yes. But the proposal, and this is for the seminar here, this proposal is only for the modeling process. What is the velocity gen process that I have to use? A priori you don't know. So first you use this formal asymptotic method, you derive your velocity gen process, the one that is going to help you to model the problem, and later on you prove rigorously that it converges to the solution. This second step we have not done yet in this case. Okay, so in the last 5 minutes that I have, sorry for that, I'm going to try to explain everything. The marginal density is independent of epsilon, so we can assume that the integral in the velocity of P1, P2, and higher, they are 0. So the mass is concentrated in P0. Let's assume that. Okay, so for the case of Bacillus Subtilis that we are interested in, I'm going to propose a perturbation of the turning kernel and turning rate, which is of Schnitzer type. Schnitzer proposed for another problem in kinetic theory the following. He said, okay, the turning kernel is going to be unperturbed. It's going to be a turning kernel that depends on V and V prime. Okay? But the turning frequency is going to be perturbed in epsilon. It's going to be a constant in V, lambda 0, plus epsilon, lambda 1 that depends on V. Lambda 0, this is very important. Lambda 0 is constant in the velocity. It's constant in V. It can depend on other things. It can depend on fixed time and space. It can depend on space and time. And for the problem that I'm interested in, it's going to depend on space and time via the chemical signal or the density of the bacteria. The important fact is that it's constant in the velocity. So the turning operator, if you use only this constant lambda 0, goes like this. So this is the first proposition. And if you take a perturbation of turning kernel and rate of Schnitzer type, then the marginal density is independent of P and satisfies this equation. This PDE for P0, the leading term for psi and T, in the interior of the domain. So this is the interior parabolic limit. And what are D and what are this WC? This is the interesting part. D is a diffusion tensor. It's a tensor that depends on F0, which is the pseudo-inverse of the operator L0 for L0 independent of V. And WC is going to be the chemotaxis sensitivity, which is given like this. This is a scalar, of course. And lambda 1 bar, it depends on V, is the average values. Okay? This is in general. If you consider a perturbation of Schnitzer type, then you obtain this. I prepare all the derivation. I will skip the steps of the derivation. I will only point out the crucial parts. The crucial part is if you substitute the Hilbert expansion and collect powers of epsilon at order 1, you have that L0 times P0 is 0. So P0 is in the kernel of L0. Since the only eigenvalue, mu0 is a simple eigenvalue, then it means that P0 does not depend on V. It's a constant. For fixed psi and for fixed tau, it has to be a constant. So this means that P0 depends only on psi and tau. Okay? And you switch the machine on and you collect powers of epsilon and epsilon squared. When you collect powers of epsilon squared, you obtain a solvability condition for the equations, and that will lead you to the mean field equation that you need for P0. Let me give you an example. The equation of order epsilon is L0 P1 is equal to this guy. If you take the L2 product in L2 of this left-hand side with 1, what do you get? You get 0. Because this product is the same as L0 star applied to 1, comma P1. But L0 star of 1 is 0. Because, as you know, if 0 is an eigenvalue of L0, then it's an eigenvalue of of an adjoint, if the operator is closed, etc., etc. Right? With the same multiplicity and all that. So the solvability condition for this equation is precisely that if I integrate in V this right-hand side, it has to be 0. Because the solvability condition in order 1 epsilon is not helpful. This can be checked that it's trivially satisfied because of the properties of the kernel. What is interesting is the equation of order epsilon squared, because you apply the same property. You integrate this in V. This is the L2 product of 1 times L0 has to be 0. So the solvability condition is that the right-hand side has to be 0 if you integrate in V. And that will give you the equation for P0. I will skip the details. At the very end, if you do the math, you obtain precisely that the equation that you arrive at P0 bar is this one. Boundary conditions. Of course, the boundary conditions that you impose on the transport equation will affect the boundary conditions that you obtain on the mean field equation for P0. But the interesting, this was very exciting. The interesting part of this analysis is that only if you assume that there is no normal flux, if you impose a non-normal flux, mass flux boundary condition for the transport equation, regardless of its form, then it will give you a no-flux boundary condition on the mean field equation. So, of course, you define the traces spaces on the solutions of the transport equation, and I will skip this part. The general form of the boundary conditions for the transport equation has this form: P in gamma minus. Gamma minus is, what is gamma minus? Gamma minus is, you have the velocity, and it has some, you take the dot product with the normal of the boundary, and if that is positive, you are in gamma plus. If that's negative, you are in gamma minus. So the incoming flux of cells, which is P in gamma minus, is going to be related to the outgoing flux of cells, which is P in gamma plus, through a boundary linear operator between the traces spaces. So you say that this boundary operator satisfies the non-normal mass flux across the boundary if this condition happens. There are no agents crossing the boundary, basically. They stay inside. Regular reflection boundary operators, these are very known for kinetic theory. An operator B is a regular reflection boundary operator if there is a mapping that has these properties. Okay? Basically, that if you have some velocity v, which is in gamma minus, then this calligraphic v is in gamma plus. They have the same speed, right? and satisfy the properties. Examples: the bounce back reflection boundary condition. There is a particle that comes here to the boundary, and it bounces back exactly with the same direction but with opposite. Sorry, exactly with the same speed but with opposite direction. My graph is misleading because I only draw the normal, no? But you can have a particle that goes like this, boom, hits the boundary, and then reflects exactly with the same speed but different direction. Another one is the specular reflection, which is the Snell law. Basically, if you come here, then it gets reflected with the same angle. But in both cases, the speed is preserved. Any regular reflection has non-normal flux. This is, I put the proof here because it's really very simple. It's just applying the assumptions. But there are other boundary conditions that might satisfy the non-normal flux, which are, I'm sure you've heard about them, the Maxwell type boundary conditions that combine the effects of reflection and diffusion. Those, if they satisfy the boundary, non-normal flux boundary condition, it's okay. You arrive again at the no-flux boundary conditions for the limiting equation. And this is the content of this proposition.
Can you have a sticky condition?
I don't know. In the Maxwell, I don't know. But I guess that it could be. I mean, the particle comes and gets stick to the boundary, right? As long as there is no flux across the boundary, I think that it works. But I don't know the details. Okay, I will skip this proof because now it comes the exciting part. Sorry about that. Which is how do you choose the turning kernel and the turning rate in order to arrive at the model that I previously presented. So we're going to assume that S is going to be the concentration of the chemical signal, chemoattractant, okay, and the perturbed turning frequency lambda 0 can be a function of space and time through via S or the density, but constant in P. This is very important in order to apply the previous propositions. Okay, so the turning kernel is going to be something very simple. It's an unperturbed from a uniform orientation in velocity space. The probability that you go from one velocity to the other is exactly the same. It's 1 over the measure of V. How do we choose V? V is going to be a uniform distribution of velocities in all directions with constant magnitude as possible. It's just a sphere. This is not interesting. The interesting part is the choice of the turning frequency. And we based our choice in two experimental observations. The first one, actually it's very recent, is that the tumbling time is low when the concentration of the chemoattractant is low for Bacillus Subtilis. I have to say that this experimental observation was made for the Bacillus Subtilis towards oxygen, not towards peptone. I did some research and I couldn't find that observation in the case of peptone, in the case of neutron. But I assume that it's not so. It's valid to extrapolate it to the case of peptone. The second observation is that to model aggregation, lambda must be a decreasing function of rho, which is something that Marco was suggesting. Right? So let's propose the following first order perturbation of Schnitzer type of the tumbling frequency like this. It's going to be a constant over rho times S plus epsilon. This is the order epsilon term. Kappa, that depends on the chemical signal. This is going to play the role of the chemotactic sensitivity function times V times the gradient of S. Here we are taking S hat, which means that the dependence of lambda 1 is going to be not only on the concentration of S, but also the gradient or other higher order derivatives. And this is what works. This is what works. So, what is it? What is the resultant diffusion tensor? In this case, since lambda is constant, then the pseudo-inverse of this operator is simply multiplication 1 by minus 1 over lambda 0. So the diffusion tensor looks like this. And at the very end, you have precisely this diffusion tensor, which is isotropic, is proportional to the identity, but proportional to the product of rho and S. One observation, this scalar quantity has the units of square length over time, which is the effective diffusion coefficient. This parameter here, sigma, which is S squared over nu 0 n, measures the hardness of the agar. Why? Because if you have a hard medium, then the velocity of the bacteria has to be low. The medium is very hard, so S has to be low. And also, the turning frequency per unit mass, which is this nu 0, should be large. I mean, the time that they spend moving with a certain velocity is low. So, lower values of sigma indicate harder substrates. And for the chemotactic term, in order just to finish, again, you substitute all your choices and you arrive at this, and you have a chemotactic sensitivity tensor, which is this tensor here, this integral of the velocity, with a chemotactic sensitivity function. This is the form of the chemotactic sensitivity, and the important fact, naturally from this process you see that diffusion and chemotaxis have to be related to each other. This derivation underlies the experimental observation of Ben Jacob, which was completely phenomenological. This chemotactic sensitivity depends on the diffusion in this fashion through the inverse, the pseudo-inverse of the operator. So, agrees with the experimental observation. I will skip this part. This is the Lapidus-Schiller receptor law, so the model looks like this at the very end. If you normalize it, you obtain the model that I presented at the beginning. I had a couple of slides adding a reaction term, just very quickly. The velocity jump process is Markovian in the sense that there is no history dependence. So it is legitimate to add a reaction term. And also, there is another assumption which is important, and is the following. The number of directional changes outnumber the birth events. So if you have a bacteria, and this bacteria will have directional changes, how many? Many more than the number of times in which the bacteria reproduces. So if that's the case, then the kinetics has to be measured in the slow time scale. So the kinetics goes like epsilon squared. So you have to add the reaction term at epsilon squared, and it doesn't affect the previous derivation. So that's why at the very end you can add simply to the resulting mean field equation the reaction term. Okay? So
that makes sense because the division process arrests the bacteria. You can assume that the bacteria is arrested in space when the division process starts.
Right.
Just in the biology.
Right.
So that limit is actually should be true.
And they change velocity many more times than the times they reproduce.
When they're not trying.
Exactly. So you make the scaling in order to get the non-dimensional model. It's exactly the same as before. And this is basically the proposition. And I thank you very much for your patience and your attention.
Are there questions, comments?
When you talk about the pseudo-inverse, does it mean that you have an equals problem?
It's a pseudo-inverse because it's only the inverse of the operator restricted to a subspace. The inverse doesn't exist because it's singular.
Wasn't zero because it's zero in value.
It has a zero eigenvalue. So it's a pseudo-inverse in the sense that only when you restrict the operator to
So does it mean that you could have many solutions or no solutions at all or what?
No, the solution, there is one only pseudo-inverse.
Only one solution?
Only one pseudo-inverse on the space. So when you consider that the lambda 0 is independent of the velocity, then you are working on that space, which is the space of constants. in that case, the pseudo inverse is well defined. If the turning kernel depends on V, then you cannot do that. So that is why the proposal of writing the turning rate as some constant in V plus some perturbation. So only for the constant in V turning rate you can do that. Because only in that space the pseudo inverse exists.
One more question
Yes.
about the sticky conditions. I was thinking that maybe one particle or whatever goes there, sticks there, another one comes and also sticks there, and maybe you have a deformation and you have a lot of mass in one direction. Does it goes against your theory or?
I don't know, but that's a very interesting question because you have to model aggregation in that case. In the diffusion has to have a negative sign somewhere. So maybe if you assume that the boundary condition for the transport equation has this gluing effect, I don't know, maybe at the end of the day doing the computations, the diffusion tensor that you arrive at is negative at some regimes or something like that. Models aggregation. That's interesting.
Well, maybe with the scaling factor. So if the stickiness was modeled simply as a decrease, a drop decrease in speed when you hit the boundary, maybe the aggregation will be an emergent property of the system because they get slower, and if they get slower, the next ones come in, and at some point they can't move, like in traffic problems.
Right. But that would be, I think, in another regime. Because once you
It starts to dance.
yes, it starts to be too dense. And I guess that the assumptions here and the measurements of the parameters, they change.
There are no other questions or comments. Let's thank Ramón again.
Thank you.